Hello everybody. So in this video we're gonna start with the second step of the partial differential equation toolbox, which is after doing the geometry is let's go here and check. It is the defining the boundary conditions and then defining the partial differential equation as well. So to do this, we will apply this on one of the problems that we have already solved before in the mass transfer course, and this is a problem that we didn't actually solve, but we got the simplified equation of continuity for this system. So this system is just some parallel disks, and we have diffusion of species that is taking place between these two plates here. We have constant concentration in these boundaries here. We can take a look here. These are the assumptions that we had, and just to make it clear, or the points that are of interest to us clear, that we have two disks here. We have a gas that is flowing from the top and from the bottom, so the concentration at the top and the bottom is always constant, which is Ca node, and the concentration on the surface of the disk is constant as well, which is Ca S. And there is a concentration gradient in the radial and in the z direction. So this is in short what the problem is about. And here this is the final form of the equation. We will not need to use this form of the equation actually, because we will start with the general form, or the software already has it built in, and we just need to define the inputs well. So all these are related to the manual solution or the manual simplification of the equation, but the points of interest to us are the boundary conditions that we have, which are the points that we are interested in now. So as we said, we have CAS here, CAS here, CA node here, and CA node here. So the boundary conditions are that CA at R and Z, at uppercase R, which is at this radius, and this radius, it's always CA node. So this is constant, and the other boundary condition is that at R equals 0, which is this dotted line here, this is an axis of symmetry, which means that the flux above is equal to the flux below, and that's why we'll have no flux in this place. The same for z direction. So we have constant concentration at z equals 0 and at z equals L, and this is CAS, and we know that the flux at the axis of symmetry is 0. So what we're gonna do in our solution is to solve the problem using two types of boundary conditions. First, we will use the boundary conditions that we have, which is related to the outer dimensions of the system, which is CAS here, CAS here, CE node here, and CE node here. And then we can resolve the problem taking only half of it and use the boundary condition of no flux here. So this is just to see if both will give the same outputs. In this problem here, we didn't have any numbers, so I assumed any numbers here just for the sake of solution. So I put Ca node as 0.1 gram mole per centimeter cube, CAS at 0.001 gram mole per centimeter cube, DAB as 5 multiplied 10 power minus 6, R equals 8, and L equals 20, or L over 2 equals 10. So this is or these are the values that I'm gonna use to solve the problem. So now let's go to here to the toolbox, and I have already adjusted the dimensions of the area because we have it here. It's gonna be 16 by 20, so I made it bigger to be easier for us to use. So we said it's 16 by 20, so this is I need to sorry, I forgot to snap, so let me snap first. So now I can draw it this way. It is now 16 by 20, and you can check it's 20 by 16. The width and the height are okay. and I can, like, if I want, I can move it right or left to make it centered. This will make it look better, at least for me. So now it's good now. I don't need to do anything else regarding the drawing, because I'm drawing only the area where mass transfer is taking place, the diffusion mass transfer is taking place, which is bounded by these four surfaces. So now let's take a look at the boundary conditions that we have. So we have to go to the boundary mode. In this boundary mode, I can pick any side. It says click to select boundaries, double click to open boundary condition dialog box. So this is what I'm gonna do. I know that at this side the equation is related to the concentration. Its concentration equals constant, and this is what we mentioned in the introduction here, that I'll always keep H equals to 1. And I forgot something important here, which is to make a diffusion problem. And now when I go to the boundary conditions, you'd see the equation is in terms of concentration. So it makes sense. So I'm gonna put H equals to 1, and the R is the value of concentration of interest, which is 0.1. And again, this is one important thing to notice here, is that for the values here, I made sure that they are all homogeneous from the points, from the units point of view. So all of them are in units of gram mole, and the distance in centimeter, and the time in seconds. So you have to make sure that this is homogeneous for all of them. So this is the case. I have already defined this, and I can do the same here. It's 0.1. So this is simply what I do to define the boundary conditions. It's as simple as that. And here it's it's 0.001 here, and here it is 0.001. So now I'm done with this boundary condition definition. But there is one point that's important here. So if I take a look at all the inputs here, I have already defined the concentrations, I defined the geometry, but I haven't defined the diffusion coefficient. And the reason that the boundary condition, I cannot define the boundary condition, because it's not a boundary condition related information. It is a partial differential equation related information. So I have to go to the partial differential equation mode and define the inputs that I have. So the default is 1 and 1. And again, it's not with the specific dimensions or units. So you have to make sure that you put it in the right units. In the case that we're solving, it is a steady state. So if you're choosing the type of the equation to be parabolic, then you have C dash, which is the time dependence term. So this is not our case. So our case is steady state, so it's elliptical. And here I have the equation, and as we said, Q represents the reaction or the generation term, which is called the volume source. So you don't have any reaction, so I'm gonna make the volume source is 0. And as we said, this is I think it was 5 multiplied by 10 power minus 6. So I'm gonna make it 5e minus 6. Oops. So now I have the diffusion coefficient defined. I have the partial differential equation already defined, and I have the boundaries conditions defined. So if we go back to the solution steps that we should follow, so we are done with the defining the problem geometry, we are done with the boundary conditions, and we are done with the partial differential equation here. So this is like very good. We have already done almost 60% of what we need to do. So the next is to create space increments for integration, and this is gonna be the topic of the next video. So I'll see you then, inshallah. Goodbye.